Welcome to Tales from the Periodic Table. I'm your host, Ron Hipschman. In this presentation, we're going to briefly depart from our description of the elements and do a short video about the periodic table, its history, and why it looks the way it does. I want to thank Paul Danstep for the use of a few of his great visuals, and of course, Theodore Gray for all of his spectacular books, photos, and videos of elements. This is the periodic table in its present form, designed by Theodore Gray. It's one of my favorites. You've probably seen this type of chart hanging in front of your classroom when you took chemistry, and you probably take it for granted you've seen it so many times and for so long. But where did this odd-looking table come from? Every square on the periodic table represents a different kind of atom, and these are all the atoms we know about right now, 118 of them. You can think of these as an ingredient list, and there are many recipes and many ways to cook these ingredients together to make everything in the universe. These are the raw materials. These are all we have to work with. Let's compare this to an earlier table of the elements that was used by the ancient Greeks. It's much simpler, but this is what we used to think the entire universe was made out of. Everything was either fire, water, earth, air, or some combination of these. An early attempt to improve upon the four-element system was made by Plato in his dialogue Timaeus, where he introduced these 5 shapes, which are now known as the Platonic solids. If you look at any one of these, all of the edges are the same length, all of the faces are regular polygons, each face is the same polygon, and the same number of faces meet around each corner. So these are as regular as a three-dimensional faceted shape can be. And the Greeks knew that these were the only 5 shapes that had that degree of regularity. So Plato thought, well, maybe that's significant. Maybe I can use that to explain why the elements are what they are. For example, maybe fire is a tetrahedron. If you could zoom in on a flame at a microscopic level, maybe you'd see just a bunch of elemental tetrahedrons floating around. And the reason fire burns you is because when you touch it, you're actually getting micro-stabbed by all these tiny, pointy things. Maybe the big round one, the icosahedron, maybe that's water, because it won't stack up. It'll kind of spill and roll, and maybe the fluid nature of water comes from the shape of these atoms. Maybe Earth is a cube, because cubes do stack up well, and maybe the solidity of matter comes from the fine packing of cubes. And maybe the octahedron is air because, well, something has to be the air. The dodecahedron, with its 12 sides, may represent the 12 signs of the zodiac. It's space itself. It's the container in which all these other shapes combine to form the material world. And then Plato goes on to try to do a kind of natural science with this idea. So he looks, for instance, at lightning. Maybe it's a kind of fire, so it's full of tetrahedrons, and it's combining with the air, which is octahedrons, and that gives you a lot of triangles to work with. So, for instance, if you take one atom of fire with 4 triangles, and you add 2 atoms of air, each with 8 triangles, that gives you enough triangles to make 1 atom of water with 20 triangles. So that's a theory about where rain comes from. The beauty of this theory is it's totally wrong. But at the same time, Plato's trying to do a lot of really interesting things. He's trying to understand the seeming arbitrariness of the natural world using a mathematical idea. And while he's incorrect, this is going to turn out to be a winning strategy for understanding nature. But he's also doing something that a number of Greek philosophers had done up to that time, which is he's looking really closely at matter and saying, What's going on down there? We know what was going on down there. It wasn't little polyhedra, it was actually the atoms of the periodic table. Antoine Lavoisier, who deserves a complete presentation of his own, devised a list of 33 simple substances in 1789. He believed these substances could not be broken into more fundamental parts. It was a good start at classifying elements, even if he was mistaken on a few of them. He included in his list light, caloric, a supposed heat fluid that flowed from hot to cold substances, primary elements such as oxygen, nitrogen, then called azote, and hydrogen, the nonmetallic elements, sulfur, phosphorus, carbon, and 3 acids, sulfuric, boric, and hydrofluoric, and the metallic elements, antimony, silver, arsenic, bismuth, cobalt, copper, tin, iron, manganese, mercury, molybdenum, nickel, gold, platinum, lead, tungsten, and zinc. There were also a few oxides, or earths, they couldn't reduce at the bottom of his list: calcium, magnesium, barium, aluminum, and silicon oxides. Not a totally bad set of classifications. The ancient Greeks thought about the fundamental building blocks of nature as abstract concepts of elements. Lavoisier insisted that one could only determine the nature of the elements by experimentation and observation. His list and classification was a really good start, though it was entirely qualitative rather than quantitative in nature. Unfortunately, the French Revolution put the aristocratic Lavoisier under the guillotine at the early age of 50, a tragic loss. 28 years after Lavoisier made his list, in 1817, German chemist Johann Wolfgang Dobereiner found several sets of 3 elements, like these, for example, that were chemically similar. He called these triads. Within these triads, he could predict the approximate weight of one by taking the average of the other 2. Let me demonstrate. For instance, the elements calcium, strontium, and barium were chemically similar. They all participated in very similar chemical reactions, and the chemicals exhibited many similar properties. Atomic weights are roughly what a quantity of an element would weigh if you had the same number of atoms of each. Calcium has an atomic weight of 40.078 units. The units don't matter here for the time being. Barium has an atomic weight of 137.327 units. Dobereiner noticed that if you took the average of these 2 atomic weights by adding them and dividing by 2, this resulted in an atomic weight of 88.7025, very close to the actual measured value of 87.62 units for strontium. By 1829, Dobereiner had discovered more triads in which the atomic weights could be roughly calculated by taking averages which closely matched the true atomic weights of these elements. This was an early indication that something interesting and quantitative was going on. British geologist John Newlands was the first person to invent a periodic table of the chemical elements arranged in order of their relative atomic masses in 1863. He eventually published his work in 1884. His table looked like this. He became somewhat obsessed with the fact that the element properties seemed to repeat about every 7 elements, at least for the early elements. Here you see hydrogen, 1, followed by fluorine, 8, chlorine, 15, cobalt and nickel, 22, for some reason in 1 square, followed by bromine, 29, palladium, iodine, 42, and platinum and iridium. If you look at a piano keyboard, since there are 7 unique notes on a piano, well, white key notes anyway, he called this his law of octaves. There were some interesting groupings in the first rows. For instance, notice the highly reactive halogens, fluorine, chlorine, bromine, and iodine, all in the top row. But there were other elements that should not be associated with those, and are in fact some of the most inert of the metallic elements. Similarly, in the second row, we find the alkali metals, lithium, sodium, potassium, rubidium, and cesium, but also other transition metals that should not be associated with these explosive elements. In the end, it was mostly numerology and high hopes, but a good attempt at organization. His work was not accepted by chemists of the day. De Chancourtois, I'm not going to mangle his name any more than that, was a French geologist and mineralogist who noticed that certain qualities of elements seemed to repeat themselves. In 1862, 7 years before Mendeleev, he devised a chart wrapped around a cylinder. He called this a telluric helix because tellurium was the element in the middle of the graph. De Chancourtois ordered the elements by increasing atomic weight vertically, with similar elements lined up underneath each other. Here is a flattened out version. It's quite long. This brilliant insight was an early hint that something about the elements was periodic. Unfortunately, like Newlands, he didn't attract much attention from chemists, because he was only a geologist. Julius Lothar Meyer, a German chemist, also built a really useful table where periodicity was a major factor. In an 1864 publication, he arranged his table partially in order of atomic weight, but also took into account other factors such as valence. His vertical columns contained elements with similar valences and chemical features. Note that Meyer left spaces for elements yet to be discovered. This was very close to what Mendeleev would publish 5 years later, and there's some validity to the claim that Meyer was really a co-inventor of the periodic table. Which brings us to Dmitri Mendeleev. Like Lothar Meyer, he was also trying to make sense of how the elements related to each other. Here is his handwritten periodic table in 1869. Let me magnify the important bits for you. It's kind of like our periodic table, but turned on its side. It might be easier to read the German printed edition of this, and maybe even easier if I redo it for you. Moving from top to bottom and left to right, Mendeleev arranged the elements in atomic weight order, but tried to keep the rows consistent with the chemical similarities between the elements. For example, we see the alkali metals, lithium, sodium, potassium, rubidium, and cesium in a row. Thallium was mistakenly grouped in this family. We find the chalcogens, oxygen, sulfur, selenium, and tellurium properly grouped. He did a pretty good job with the transition metals, with only a couple misplacements. An important aspect was that Mendeleev knew that he didn't know all the elements, and he left some empty spaces where he believed elements were yet to be discovered. This version of his table is a bit hard to visualize, but he did publish another that turned things by 90 degrees and brought it closer to what we normally see and are used to. In this version, the families of chemically similar elements are in vertical columns. Notice some of the holes he left in the table. One with a predicted atomic weight of 44 below boron. Another with a predicted atomic weight of 68 below aluminum. A third below silicon, and another below manganese. He called these eka-boron, eka-aluminum, eka-silicon, and eka-manganese. Eka was from Sanskrit for one like. These elements were eventually discovered. They were eka-boron, or scandium, named after Scandinavia, discovered in 1879, eka-aluminum, or gallium, named after France, discovered in 1875, eka-silicon, or germanium, obviously named after Germany, discovered in 1886, and eka-manganese, or technetium, the tech from artificial, since this element has to be made in nuclear reactors. It was obviously discovered much later in 1937. Mendeleev was not only able to predict the existence of these elements, he was also able to predict their chemical properties as well. Here is a comparison between Mendeleev's 1871 predictions and the now known properties of gallium. Note the low melting temperature of gallium. Unlike M&Ms, it melts in your hand. Note also how close all the other predictions came to the real values. The predictions for eka-silicon, or germanium, were also very close to the actual values. This was a real triumph for Mendeleev. It wasn't all perfect, though. If we look back at Mendeleev's first table, we can see some problems. For instance, notice that tellurium and iodine are in reversed atomic weight order. By the way, he used a J for the chemical symbol for iodine. This was a problem because Mendeleev knew that chemically, iodine should be in the halogen row, and tellurium should be in the chalcogen row. He could not justify this inconsistency. The answer had to wait until 1914. Henry Moseley, a British physicist, using X-rays was for the first time able to accurately determine the atomic number of the elements. The atomic number is the number of positive charges, now known to be protons, in the nucleus of the atom. He determined that the periodic table should be arranged by atomic number rather than by atomic weight. Mendeleev's arrangement of the elements by atomic weight, which also included the neutrons of the nucleus, unknown at the time, is what caused his ordering inconsistencies. Moseley's measurements and suggestion completely solved this problem. Niels Bohr's pioneering work in quantum mechanics, don't worry, we're not going to delve into that further, led him to describe electron shells and energy levels within the atom. Here you see some of the shapes of those orbitals. He defined the various classes of orbitals and their energies, and how they were populated by their resident electrons. These four types, the s, the p, the d, and the f orbitals, allowed him to arrange the periodic table into our familiar shape. Here's that shape. This is a convenient form, easily printed on posters and inserted in books. However, that island below the main table hides some of the beauty of Niels Bohr's work and should properly be placed within the main table like this. This is known as the long form of the periodic table. Now, let's incorporate Bohr's orbitals. Remember Bohr's orbital classes, the s, p, d, and f shells. Each is filled as we move up the periodic table. We can see that each is responsible for a section of the table. An s orbital can hold only 2 electrons. The p orbital can hold 6 electrons. The d orbital can hold 10 electrons, and the f orbital can hold 14 electrons. There are arguments concerning the placement of hydrogen and helium in the periodic table, but these are really edge cases we can ignore for now. Let's look at a few examples and how the atom's electron configuration is notated. Hydrogen in row 1, or properly period 1, has 1 electron in the s shell and is notated 1s1. Row 1, s shell with 1 electron. Helium is 1s2. Row 1, s shell with 2 electrons, all it can hold. Lithium in row, or period 2, has to populate another shell. 1s2, 2s1. Beryllium is 1s2, 2s2. The second s shell is now full. We start work on the p shell. Boron 1s2, 2s2, 2p1. Next is carbon. 1s2, 2s2, 2p2. We'll skip a few until we reach neon. 1s2, 2s2, 2p6, a full p shell. Lather, rinse, repeat until we reach the most complicated element known right now, 118, oganesson, which looks like this. Bohr's orbitals define the shape of the modern periodic table. What other patterns can the table show us? Let's go back to the more classic short-form table and have a look. The east coast of the periodic table have elements with completely filled shells. They are the inert or noble gases. The west coast, with the exception of hydrogen, contain the highly reactive alkali metals. They're highly reactive because they all have a lonely S-shell electron hanging out in the breeze that would love to react with just about anything. Most of these explode when submerged in water. The complement of the alkali metals are on the other side of the chart, the halogens. These elements are missing a single electron from their outer shell and are desperate to snatch one from another atom. Like the alkali metals, these are all dangerously reactive, and some scientists lost their lives researching them, especially fluorine. One column in from the alkali metals, we find the slightly less reactive alkaline earth elements. These elements would have to lose 2 electrons to have full shells, and hence have a valence of +2. Likewise, with the elements one column in from the halogens, called the chalcogens, these elements want to gain 2 electrons, and have a valence of -2. They all share similar chemical qualities. The F block below the table contain the almost indistinguishable rare earth elements, or lanthanides, named after the first element of the row, lanthanum. These elements aren't really very rare, they're just hard to chemically separate. And the actinides below the rare earths, named after that row's first element, actinium, are all radioactive. The nonmetals, again with the exception of hydrogen, which could be placed above fluorine with some justification, all occur on the east coast of the table. The dividing line between the conductive metals and the non-conductive nonmetals runs along this diagonal and make up the semiconductor elements that make all our electronics possible. The central portion of the table is filled with the transition metals, or D-block metals. These look like metals, they're malleable and ductile, they conduct heat and electricity, and they form positive ions. You're familiar with several of them: copper, silver, gold, iron, cobalt, nickel, zinc, and others. Here are the solids at room temperature, and the liquids at room temperature. There's only 2 of those, bromine and mercury. And the gases at room temperature, most on the east coast of the table except for that troublesome hydrogen, but remember, there's some justification it can be placed in the halogen column. The north coast is populated with all these stable, non-radioactive elements, with the exception of technetium and promethium. And the south coast with the unstable, radioactive elements. This isn't the only shape people have invented for the periodic table. We've already seen de Chancourtois' helical design. This is a wild roller coaster-like version from the physicist William Crookes, made in 1921. Since it's a periodic table, here's a circular version starting with hydrogen in the center. This is sort of the same thing, but the lanthanides and actinides are included in the circles like the long form we previously talked about. This circular version looks like a Mayan calendar a bit, but is confusing because the families of elements aren't very obvious. This one was designed by Mitch Fincher. Here's a circular version that has hydrogen on the outside and does a good job displaying element families. You probably recognize it's really just a bent version of the long-form table. And then there are the spirals. This one with hydrogen in the middle and spiraling out by Jan Scholten. This similar version is like a pyramid seen from above. I suppose you could do a three-dimensional version of this too. Here's another spiral, with hydrogen on the outside spiraling inward by Robert Harrison. And this low-B spiral version that tries to deal with the lanthanides, actinides, and transition metals by Theodore Benfey. And yet another low-B version that should appeal to auto racing fans by Franklin Hyde. And this unusual spiral using hexagons by Jeff Moran. And finally, one called the Mendeleev flower, made from paper. There are many, many more. If you're interested in learning more about the periodic table, I can recommend Theodore Gray's The Elements. For an in-depth book, try Eric Scarry's The Periodic Table, Its Story and Its Significance, or the bite-sized version of that book, The Periodic Table, a very short introduction. No matter which way you choose to view the periodic table, I hope you're as excited about it and have learned as much from it as I have. This is the stuff that makes up the entire universe, including you and me. I'm your host, Ron Hipschman, and I hope you'll join me for future episodes of Tales from the Periodic Table.